Okay, so again, thanks for the invitation to speak here. My name is Hod Finkelstein. I'm a Chief R&D Officer at AI and LiDAR company. And I will be speaking about artificial intelligence with advanced photonics boost, high resolution, 3D vision up to a kilometer away. In terms of the structure of my talk, I'll start with the very basic fundamentals of how LiDAR actually works. Then I will move on to discuss some of the main system architectures for LiDARs. And then I will discuss in some more detail AI's adaptive sensing using deterministic artificial intelligence, which is the unique approach that we are taking to address this very tough challenge of automotive LiDAR. And I will conclude my talk with some performance videos to show how the system actually operates in real life conditions. So first of all, how does the LiDAR work? So LiDAR measures the time of flight of light in order to provide the position and reflectivity of objects. So basically all LiDAR systems have an emitter that you can see here, a receiver, and they send some form of light, whether it's pulse light or CW or amplitude modulated or frequency modulated light. And the system measures the time it takes that light to travel to the detector and back, and sometimes additional information such as the intensity of the echo, the Doppler shift, etc. Now, typically when we look at how well a LiDAR system actually performs, at least in the automotive field, automotive OEMs typically specify performance for a 10% reflective Lambertian target. Clearly, a more reflective target, you can see it much farther away. The performance must be in bright sunlight, and specifically at 100 kilolux of sunlight. Equally important is what is the probability of detection. So if there is a target and you try to image it n times, what percentage of those times are you actually going to detect it? And then what is the false alarm rate? So again, all of these are knobs that can be played, and really the relevance of a specification of a LiDAR system is only when all of these specifications are defined concurrently. Now, next, I want to go over some of the main LiDAR architectures out there. And the first one, I call them the spinners. These are more formally known as the rotating LiDARs, and I'm sure a lot of you have seen them. And these were really the first ones to be demonstrated in the market. They were actually invented, I would say, by students in the DARPA challenge in the 2000s, really using off-the-shelf components. So they took some lasers, they took some detectors, they built some mechanics, and basically they started spinning those devices around. You can see a picture on the top right from the DARPA challenge in 2007. These systems are still quite popular today. If you look at systems today, they look not very different from the 2007 systems. These LiDAR systems typically cover 360 degrees, which is good, but sometimes, if you want to mount the LiDAR in the front of the car or on the side of the car, you don't really need 360 degrees. One of the main challenges is that they trade off range for frame rate, because you have to wait for the echo to return from the farthest target before you move on to the next position, and you're continuously rotating. The vertical resolution is achieved by packing more lasers in the rotating head shown below, and that means that the system is not really very scalable in terms of its resolution, because there are only so many lasers you can pack in a laser head. And these systems typically suffer from relatively low reliability, and it's really the mechanical gears that typically are first to fail, and they're also susceptible to vibration and shock. So some of the newer systems are what I call the gazers. They are also formally known as flash LiDARs, and those systems simultaneously illuminate and image the whole field of view. There are actually very few real flash LiDAR systems out there in the market today. In fact, the only one that I'm aware of that is true flash is the Continental LiDAR system. The other ones call themselves flash, but they play games by sequentially acquiring a signal. So while those systems have no moving parts, they do suffer from three fatal flaws. The first one is that they illuminate the whole field of view basically with almost uniform power. And that power is defined by the dimmest, farthest object that the system needs to see. And therefore, these systems waste a huge amount of power because obviously you're not going to have the dimmest, farthest object in the brightest sunlight everywhere in your field of view. And yet you illuminate with that maximum power. They also image a relatively large field of view with fine resolution, so they require very expensive optics and large detector arrays. And probably most critically is because they illuminate and image a very high dynamic range scene at once, both a car tire and a retroreflector, for example, they are susceptible to stray light. And we can see that in the images below, where you can see a license plate. And because that license plate is reflecting a lot of the laser light, you have blooming or haloing effects. And those can be even worse in more challenging conditions. So gazers really offer a very simple architecture, solid state, no moving parts, but they would typically come with an inferior cost and with higher power consumption and larger size. That brings us to the more prevalent architectures out there today, which are the scanning mirrors. And there are two types of those systems. The first one is called the monostatic architecture. And basically the way that these systems operate is shown on the diagram on the right. You have an emitter, which is a laser. The laser light is reflected through a mirror to an object. The object reflects the light to many directions. Some of that light returns back to the same mirror. And from that mirror, the light is funneled to a detector. And it's really the fact that you're using the same mirror that is important here. Now, one of the biggest challenges of these systems is that collecting enough signal requires a large aperture. But in order to basically conserve a undo, you need to have a large mirror to do the collection. However, mechanically, because you need to stop and scan at every position out of maybe 100,000 positions, directions that the LiDAR has to point to, making a large mirror means that the system is not stable mechanically. And so there are these conflicting requirements for monostatic systems, which makes them either large and expensive or drawing a lot of power so that you can achieve the target signal to noise ratio. The other challenge happens with nearby obstacles such as a windshield. So some of the emitter light is going to be reflected by those nearby obstacles and be sent back to the detector, sometimes overwhelming it. And therefore, for these systems, you typically need to mount them on the roof of a car, and that is, in some applications, undesirable. So monostatic systems have limited cost and size scalability, and they suffer from back reflection. The last architecture that I'm going to describe is also a scanning mirror architecture, but it's called a bistatic architecture or a coaxial architecture. In this architecture, we have an emitter, and the laser light is reflected again from a scanning mirror to map the whole field of view, but the reflected signal is collected through a collection lens, which focuses the light onto a detector. The benefit of this architecture is that there is no need to wait for an echo before the beam moves to the next position. And that means you can basically have multiple pulses in the air at any one time, and that translates to more 3D points per second, higher resolution, higher performance of the system. And this also enables more flexibility in the scan patterns. You can basically tell the detector where you want to, tell the LiDAR system where you want to fire, and you can send it back to a position where there is interesting information. And I will discuss that in my next slide. One of the nice features of this architecture is because you don't need to scan and stop, the mirrors can be very small. You also don't use the same mirror for the collection path. So you can have a larger lens to collect enough of the signals so that your emitter power is low, and also have a smaller mirror. So you're basically having the cake and eating it too. Now, the physical separation between the emitter and the receiver can also provide immunity to near field reflections, such as I mentioned before, from a windshield or from dirt on the target. And consequently, these systems are quite small. This is an image of a system by Continental using AI's Bistatic technology. And these systems can be integrated on the roof, but also inside the grill or even inside cabins of vehicles. Now, that really brings us to the need for intelligence in scanning. So imaging at the highest resolution everywhere wastes system resources, and that means laser power, or otherwise it undersamples the scene, which is also not so good. So this is akin to a sprinkler system that just sprinkles everywhere. You would water the grass where you need the water, but you'd also waste water on the pavement. Think of intelligence in a LiDAR system like the smart sprinkler system on the right, where you only water where this is needed. And really the programmability of the system is done in software. And so you can reprogram the scan pattern adaptively or based on the information that is found in your scene. Okay, now scene adaptation can be quite tough. There are a lot of different scenes that an automotive LiDAR system needs to look at. There are some unpredictable objects like crazy motorcyclists trying to cut you off, or a kid running after a ball, or you need to operate in adverse weather conditions. Each one of them translates to different scanning requirements from the LiDAR system. So it is quite desirable to have an adaptive scanning scheme. So what we do at AI is we initially map out the whole field of view with quite good resolution. And that resolution itself can be programmed such that in the center of the field of view, you achieve high resolution by firing the laser quite densely, whereas in the background, you fire more sparsely. But once we find interesting objects, we can go back within the frame. So within milliseconds, we can go back to those positions and map out those interesting objects at much higher resolution, giving higher reliability and higher confidence in the classification of these objects. And we call that search, which is the first phase, acquire, and then we move that information to the fusion engine of the automotive vehicle to act based on the information that has been collected. So search, acquire, and act. Next, I'm going to show you some videos of how our system actually operates. So we take these systems out to the field. We use sprinklers to generate mist. We image through a window to mimic internal imaging. And what you can see here is the water cloud in the beginning. And now we can see objects that are being mapped by the system all the way to 1,000 meters. So I'll just show it one more time. So again, there is a sprinkler system that mimics the mist, then a window that mimics the windshield of the car, and you can see the mist cloud, and then all of the objects that are mapped, and this is done in full sunlight, all the way to 1,000 meters, and we're getting tens of points per vehicle at maximum distance. Another example is imaging when the sun is right inside the field of view, which is actually very difficult in terms of stray light and other effects. And what we can see here is that even though the sun is directly in the field of view of the system, we can see the vehicles, we can see the trees and the bushes to hundreds of meters in range. And another application for our LiDAR system is in intelligent transportation. In this example, this is automated tolling to be able to map out cars, objects, other vehicles as they approach a toll gate, again, across various weather conditions and different vehicles, etc. So to summarize my talk, LiDAR sensors have to deliver reliable data across very challenging conditions in a small form factor using low power and with a low cost manufacturable product. So this is a very, very challenging problem that very few companies in the world have been able to address as of today. Now, various architectures try to address this challenge, but the problem with all of them is that they deploy very expensive system resources independently of the scene. And this results in either expensive products or underperforming ones. What we do at AI is we intelligently invest those system resources where information exists in order to provide actionable 3D point clouds. So in order to ensure the safety of the system, we map out the whole field of view. But then in order to increase the reliability and resolution, we go back to the regions that contain the most interesting information and map them out in even greater detail. Our bistatic design enables software-controlled deterministic scanning algorithms in a mechanically robust and cost-efficient system. And today, the system is being deployed in automotive, smart infrastructure, and in industrial applications. And with that, I will end my talk and open it for questions. I want to just thank one of our fans that sent us this nice AI anime object. And with that, I'll open this session for questions.
Thank you very much. It's a great talk. So once again, it's a Q&A time. You can either raise your hand or send a message in the chat, which I can read out. So start. Do you have any questions for the speaker? Well, in the meantime, while wait if there are questions, I actually had a question of my own, if you don't mind. What I missed in your talk is when you showed the picture of you can see the sun and you can see the vehicles going by. Were you doing something in the software? How are you preventing the sun from flooding the detectors? Basically, is my question.
Okay, that's a great question. So there are a number of things that we are doing actually. So one thing that we're doing is we're operating in 1550 nanometers. So LiDARs typically either operate in the near infrared at the 900 range or at 1550. The solar spectrum is much more sparse at 1550 than it is at the 900 nanometers. So that makes our life much, much easier. The second thing that we're doing is because of the scanning of our system, we are able to apply certain tricks to exclude the sun from impacting our point cloud. So probably I cannot say too much about that, but it's really, I would say, a combination. So we're not doing anything funny with the scanning itself. So we are actually scanning the regions that are close to the sun as well. But because of the wavelengths that we're operating in, because of some of the optics that we have in our system, and because of our scanning algorithms, we are able to exclude the effect of the sun from our point cloud. Okay.
And then just to continue that for a moment, of course, I guess the price to pay is the detectors you use, because now you're operating at 1550, a little bit more expensive, but
correct. So yeah. So I think there is no free lunch. I call it the law of conservation of misery. You always have to pay something, and indeed, the soft spot of the bistatic approach at 1550 is that you do need to have, in our case, it's an indium gallium arsenide focal plane array. We use it at room temperature, so we don't have to cool it. We're able to operate it at room temperature. What I can say is that the requirement of the focal plane array is much less severe than from a CMOS focal plane array because of the way that we operate our system. And also there are recent advances in the detector space that make these 3.5 or shortwave IR detector less expensive, and certainly that is part of kind of our technology roadmap moving forward.
Okay, no. Thank you very much. thanks very much for your talk. It's a great talk.
Thank you.
So we'll now move on to our next talk. The next talk is on 5G and industrial manufacturing. The presentation is going to be given by Tracy Vanek. She's with the European Photonics Industry Consortium, or more popularly known as EPIC. Tracy, the floor is yours.
Thank you so much, Araf, and thank you also, Dalma. Okay, I'm trying to share my screen now. There we go. My screen. Okay, I'm going to assume that everything is good. So with that, I'm going to be discussing 5G and industrial manufacturing. And we're going to be going fairly fast through some of the first slides to be able to spend more time on the network details themselves. So to begin, there we go, okay. So we're going to be looking at networks for manufacturing in support of Industry 4.0 and digital twins. We'll be examining private 5G networks as well as millimeter wave networks. We're going to talk about the severe timing considerations, and most importantly for industrial manufacturing processing is the timing. So, the security. So being able to secure not only the process, but the equipment. So to begin, there's a lot of changes that are happening within manufacturing these days. One of the big changes is we're entering Industry 4.0 and digital twins. Digital twins give us a way of creating a model of what we want to create. And different from CAD/CAM, where you have the model and then you would create it. With digital twins, you're going to have continuous feedback for the manufacturing process to determine how well have you done. So you're able to make continuous changes in order to compensate for the manufacturing, whether you have differences in materials or you have aging equipment. And so the promise for digital twin is that you can continuously optimize your production, which leads to increases in efficiency and increases in precision. These improved efficiencies and precisions result in improved yields with reduced cost, reduced loss of bad products, and real-time quality product manufacturing. Plus, you are able to provide critical remote process monitoring and predictive maintenance so that you can repair before you have to bring the line down and replace. The consideration, though, for these is that it requires very heavy bandwidth utilization. So if we look here, let me set up can you see my arrow, I hope? I'm going to assume you can. Okay, yes. Great. So if you look here at this diagram, this is a laser system. And this particular laser system has a camera that's built in, it has the laser power module, it can focus, and it can provide continuous monitoring and feedback for itself. So it is continuously adjusting how well it lasers the material. And this is a continuous process for this laser. But what we are looking to do with Digital 4.0 is we're looking to provide feedback on how well that process occurred. And for this, we need real-time images. So data is what drives the digital twin. So with a digital twin, you need to send this feedback from the camera up to manufacturing oversight. But we're not looking at just individual frames. We're looking at continuous monitoring of the process. So the drawback for this is that this will have extremely high bandwidth utilization. So there are many different types of vision technologies that can be used to determine how well you are manufacturing. Hyperspectral imaging is really interesting in that it can actually examine the contents, the materials that are used and made in the materials. But with Industry 4.0, robotics have a role as well. So it's not just copying a design that you want to make, but it's monitoring a robot and what you want it to do. So in the case of a robot, you may have it inspecting, you may have it doing welding, you may have it delivering parts, but you want to be sure that you're receiving this information so that you know where it is and you can avoid collision. And also too, because a robot is mechanical, it has a higher potential for degradation and failure. So you want to be able to monitor how well is it operating so that you can repair early rather than take down the line. So with many robots have LiDAR. AI just talked about LiDAR and HUD. But with this, here you can look at, use LiDAR for sensing where the robot is, how fast is it traveling, is it delivering your parts to the line on time? So it gives you information that are necessary for process control. And there are even autonomous robots for manufacturing. You think of autonomous vehicles. Well, now there are autonomous robots that can have good information that they receive via LiDAR that they can use to determine exactly what is around them to make more intelligent decisions as they move around the factory floor. But these also have to be monitored. So as a result, we have a lot of potential bandwidth coming in from both camera systems for each individual process, for robots, and for movements within the manufacturing floor. So with Industry 4.0, the benefit of Industry 4.0 is improved efficiency. And with this, you have safer factories, you have equipment that is interconnected, and it's not just a one-way feed, it's a communication that is bidirectional. We have created a potential for a much safer environment for humans where you automate unsafe processes or do very high precision, difficult work. And then we can use on top of this intelligence like machine learning or neural networks or even artificial intelligence to improve the process. But this requires a lot of bandwidth. And so the technology that shows the best promise to be able to support this bandwidth is 5G, because it has no cables, you have the bandwidth available, faster communication, lower latency, and it can connect processes, IoT sensors and video, robots, et cetera, and it also provides improved detection of timing inefficiencies, which would potentially reduce yield. So this is a private 5G factory. And on this private 5G factory, you see these little radios here. These are little massive input, massive output, beam steered radios that are used to generate the the 5G signal. And in this case, this would be the 5G signal, the 5G network that is being created by the use of these antennae. And it communicates to a 5G core network that would be owned by the company. But you'll notice that this is a flat network architecture. There are no stops here. There is no segmentation. And in a 5G manufacturing environment, you want to be sure that each subsystem of the manufacturing floor is segmented in the case that there should be a breach. So you want to use firewalls, and that was not part of that private 5G network, but part of it is because it's difficult to implement. So the other alternative is to use millimeter wave for manufacturing. So here we see this was the bandwidth for 5G. Millimeter wave has much higher bandwidth potential. So we have higher bandwidth with much lower latency. However, because it's higher frequency, the higher the loss, so the shorter the distance. But one of the advantages that millimeter wave can be used for, especially on initial implementations, is using millimeter wave as a wireless backbone. And it's already entering the market. There are a number of different factories that are utilizing millimeter wave. And in fact, here we have from Avanti, we have a phased array antenna, a small massive input, massive output MIMO antenna that can be used and was designed specifically for millimeter wave in industrial areas. So why not Wi-Fi 6? And this is for Dalma. Why not Wi-Fi 6 for industrial manufacturing? Well, the biggest problem with Wi-Fi 6 is that it doesn't have the same bandwidth that you want. Plus, it's very susceptible to motor noise, which tends to occur on a floor. Wi-Fi 6E, however, looks very interesting, but it still has less bandwidth availability than millimeter wave. Now, with millimeter wave and with 5G in general, timing is crucial and synchronization is crucial. And we see that synchronization is also critical for Industry 4.0 because we want to be sure that items arrive just in time to be manufactured. And so we need to make sure that we're using orchestration. And we have time-sensitive networks that enable this and other applications requiring the synchronization. And within manufacturing, timing and synchronization equals money. So very often you have the product of one process or one manufacturing step that is required for the next. So maximum yields require that there be no delays. And you want to make sure that you have the highest number of saleable products because that increases your revenue. And with 5G networks, they have such high frequencies. We have very stringent timing requirements. We're no longer looking at microseconds. We're looking at we're no longer looking at milliseconds, we're looking at microseconds. There we go, excuse me. And for timing and synchronization in 5G, this is all critical. Now for a typical 5G network that would be out in the field, you would have at each antenna, at each base station, you would have a GPS or a GNSS that would be used there for that reference for the time. But given the vulnerability to these GPS satellites and the fact that they can be spoofed or jammed, now we're starting to see more centralized timing networks that are being implemented. Many of them are based upon cesium clocks and other timing like White Rabbit that helps to correct for any timing discrepancies bidirectionally. And we need to make sure that we have switches and routers that are able to operate in time-sensitive network. So if you have a large factory, this is probably something along the lines that you want to do to ensure that you have the best timing and synchronization available for your processes. So we mentioned before, one of the areas of concern in this model is that it's flat architecture, and the key concern is security. So we're looking at two different religious approaches almost. For a LAN network, which is what we're used to seeing in an enterprise network, it's segmented, and we have user credentials and identification. We use firewalls, maybe intrusion prevention systems, and we monitor the traffic to see if there's any changes, any odd traffic patterns that might indicate a breach. But in the WAN, think about your cell phone or the phone companies. They're focused on connecting. It's a very different philosophy. They're flat networks. The connection is to the carrier only, and permissions, the only permissions are really billing, perhaps long distance charges, message rates, overseas charges, et cetera. So the security systems are carrier based, although you may have some skilled users that are implementing anti-malware on their phones. But in 5G manufacturing, in industrial manufacturing, the security of the processes is paramount. The process control equipment must be protected because it represents a huge investment from millions and millions of dollars. Two, the activities must also be protected, because if you have a breach that occurs, you can either sour the manufacturing process so that you have unsaleable product, or what many hackers are trying to do, or it's far more nefarious, they are trying to actually cause something to go boom. So you must keep control of security of the manufacturing process, not only for the processes, not only for the product, but also for the people. So there is a network architecture that has been created to help protect industrial manufacturing environments. And this happens to be the Purdue architecture. It's designed to help safeguard the crown jewels, the process equipment. So you have layers of protection. But when we're looking at process control segmentation for safety, when you're deploying a 5G network, you have to take very extreme care in order to provide these segments. And again, for a telco network, for a 5G network, segmentation is not something that comes naturally. And so this is something that needs not just a vendor that comes in and says, I can connect you up with a private 5G network. You need someone who has the experience that understands the SCADA infrastructure that is required for industrial manufacturing. Now, taking a sidestep here, for industrial IoT messaging, and I'm just going to refer to it as IoT for this presentation, you have a potential variance in the size of message sizes. So you have many little tiny messages that are time sensitive, but then the real-time camera images are as well. And for those camera images, you need quality images so that you can see exactly how things are progressing. So things like meters and sensors, they tend to be small messages. Those are like pressure status, leak detectors, valve failures, et cetera. But anything that involves a camera or a video, these are large messages. And unlike AI, we're not looking at capturing an individual frame periodically. We're looking at the entire video feed, although that can be compressed. So, but the key thing involved with industrial control systems is that for both of these different message sizes, they are all time sensitive. So why are we talking about IIoT? Well, because how are you going to connect millimeter wave? So it's one thing to talk about the network, but what's going to connect to it? You're not going to be connecting your phone to it. Instead, you're going to be connecting the manufacturing equipment. So how are you going to evolve this connection? Well, two good places to begin are either with the PCs that are used for process control and monitoring, or with the IoT devices. either one is a good place to start, and there are a number of different IoT devices that are millimeter wave enabled. Process equipment will take longer because that's a large investment and it tends not to be replaced frequently. But the thing to keep in mind with security is that any device or any communication can be spoofed, and we want to make sure that that doesn't happen, especially with IoT devices. So how do you integrate IoT devices in with time-sensitive information? Well, you can either use the existing structure and have IoT devices that communicate within that structure, or it's possible to do a separate communication that possibly is based upon millimeter wave, where you provide a direct communication to manufacturing operations, and this way you ensure that the information is provided in a timely basis. The problem is how this could potentially be a highway to a breach for your process equipment. So you need to make sure that you are providing excellent security, not only for these IoT devices, but also for the access to the process equipment layer. So securing the network is not enough. Doing encryption on devices is not enough. You need to have all elements in order to provide security for this network. So providing an IoT device, how do you secure it? Well, one of the easiest things is you buy a chip. So it's going to increase your BOM, but this way your product will be security enabled. And you want to be sure that it can not only do firmware updates and have a unique ID, not all of the same family. You should have all of the same family of IoT devices should have the same ID, but you want to be sure that it can do cybersecurity event logging. And another thing that's coming up that's very interesting is something called PUF, physically unclonable function. And each chip is different in minute ways. So it can be an arrangement of small impurities. It can be the lamination pattern on the top of the chip. It's unique for each device. So it's very subtle. It's hard to observe, especially if you're not sitting right on top of the chip. And the PUF-based key does not exist in memory, so therefore it cannot be stolen. So, and there is a potential to build PUF with a very small hardware investment. So I think I made it. Photonics is playing a key role in emerging industrial manufacturing requirements. We see that we need to have very large bandwidth in order to support Industry 4.0 and digital twin. Two areas that look very promising are private 5G and millimeter wave. We have to be sure that we have taken into consideration a good timing source that will be able to provide accurate sync, and that we are providing security for the entire manufacturing process with security architectures and secure device implementations. And with that, I'm with EPIC, and EPIC is the European Photonics Industry Consortium. We have over 750 member companies right now. And what we do is we get to know the different companies and the technology, emerging technologies, and we help to make connections between component manufacturers and packagers and system integrators to enable product development. And with that, thank you so much. Questions?
Thank you, Tracy, for it's a great talk. So questions, of course, you can raise your hand, or we're still in a small enough group where you can start asking a question directly if you'd like. Or of course, use the chat message if you prefer. Tracy, I'll ask a question, while others might be preparing to do so. So I know you focused a lot on security, and rightly so. For millimeter wave, do you see other challenges that beyond what was discussed?
Absolutely. So with millimeter wave, the installation is very critical. It has a short distance, so you have to ensure that you have a clear path for the area that you want to cover. And along those lines, a millimeter wave can be blocked by objects. So if you have a large metal that's used in manufacturing, you'll have to arrange the antennas so that you're not trying to broadcast through a large body, and it can be blocked. So key is to keep the path for millimeter wave clean so that you can reach the bandwidth that it's capable of.
Okay, no, thank you. So any other questions? All right, Tracy, thank you again. Move on to our next talk. So our next talk is on IP optical integration with 400 gig ZR Plus. The speaker today is Tiberio Gregorio with Nokia Networks. So, Timmy, floor is yours.
Thanks a lot, Aref. I hope you can see the slides and hear me. My name is Tibi Grigoriou. I'm Senior Director with Nokia Network Infrastructure, Strategy and Technology. And for the next talk, we'll remain in the telecom domain. And we're going to look at how 400ZR coherent optics is shaping the integration and interworking between the IP and optical domains. First, we're going to look at what's IP and optical integration and what's new this time. As you learn, we've been doing this for quite a bit now. And at the end, we'll look at how the 400ZR coherent optics is actually impacting the network architecture. So first, let's look at the domains. If we look at the IP domain, the problem solving is in digital domain. All the protocols are open. We have a number of standard bodies, IETF, for example, and where the industries meets and decides what are the interfaces. And the end result is a system that is most likely plug and play. Yeah, it's done in a interoperable open APIs type of system. If we look at the optical domain, the problems there are mostly electro-optical type of problems, requires very complex algorithms, and most of the time has influence from outside plant, right? It's the type of fiber, type of connectors that impact the whole design. So the overall result is a system that is most likely having a lot of proprietary technology inside, and is extremely specialized and requires a specialized type of engineering and support to actually install, debug, and maintain. So if we have a look at the end result, on the left side, we see an example of an IP routing, and what you see there is kind of a dense mix of ports, like you see 36 ports, 400 gigs, so very dense type of architecture. On the optical side, the focus is on spectral efficiency. So this doesn't mean that necessarily the systems are kind of small. Obviously, there we have larger 20, 30 RU systems, but the idea is that mostly the line cards are focused on spectral efficiency and moving as many bits as far as possible, right? So it's a different type of optimization that we're attempting. So in the past, we've been talking about IP optical integration for over a decade now. And we did try during the this evolution, different type of integration. So we tried to do IP over DWDM. So this is basically optics cards in a router. We tried that. Limited success, just because the silicon performance was higher than what the optics could do. So basically this implies a router density penalty. Then we tried the other way around. We ported and we did some of the routing code, and we integrated that into a optical system. So again, here we had mixed success, right? It was very useful for some of the layer 2 grooming, but then was basically mixing water and oil. It didn't work very well. We experimented with some sort of a management, common management thing, where we had the router manage the optical shelf and change some of the parameters that didn't have too much success. And I think the most successful combination to date is the SDN controller, where the layer, the IP layer, the networking layer, and the optical layer are managed together in a coherent way from a software-defined networking type of controller that knows both domains and optimizes the application based on that requirements. So what's new? Why we're trying to redefine the IP optical interworking? If we look at the two domains, the packet and optical technology, what we see is that the working framework for innovation is approaching the physical limits. This is both in the silicon and the optical side. Also, what we notice is that the rapid advancements that we had in the coherent optical and silicon fabrication is slowing down. We still have advancements, but we seem to be they seem to be delivering improvements at a lower pace. And as we can see from Tracy's presentation, there is a lot of bandwidth requirements. The bandwidth is growing by a lot of applications. We have broadband applications, we have industrial applications. So what we see from an industry perspective, there is a relentless cost optimization pressure from the IP optical perspective. There is improvement, and we're improving the cost optimization, but what happens is we're not keeping pace with the requirements. So I think we're experiencing an inflection point where the technology gains will have to come from a different source than we've been doing in the past. So for an example, I really like the optical transmission performance. This is kind of a nice chart that shows the previous concept that you talked about, right? If you're looking at the efficiencies that were achieved, we got like 15 dB in 7 years, and then another 10 in 13 years, and it's very little left. Definitely, there's research ongoing, but you reach a point where it's kind of diminishing returns, right? It's going to be a lot of work and a lot of investment to kind of close that gap. So this is what we believe is the inflection point, where instead of focusing on transmission performance and more efficient spectrum efficiency, we now switch to a more power and space cost efficiency type of designs and architectures. So let me see. So what's new? Let's look at how the 400ZR Plus is impacting the IP and optical domains. On the graph, with the dark line, dark blue line, we see the client pluggables that are coming into the router. So a typical design would be client routers, plugged in router cards, and then client plugs in an optical system, and then from there transponder. So what you see on the client side of the router is mostly kind of going more and more dense. On the line side, which is the light blue color, we see that the line side is actually converging, so that we have a point with 400ZR Plus in QSFP-DD that it matches the client form factor and the line side form factor. So what that means is that from a router perspective, there is no density penalty anymore. From an optical perspective, it means that the capacity to fill a wavelength is met. So it's a very nice match where the silicon density on the router side matches the fiber efficiencies on the optical side. Couple of standards that are tracking the 400ZR Plus. We have the OEF standard. This is the 400ZR standard. And then there's a number of MSAs with 400ZR Plus that is building on top of the 400ZR attempting to increase the reach using the OFEC. And we have OpenROADM that actually it's building on 400ZR plus, adding full feature client mapping. So this is not only IP traffic, but it's a full feature client. One more trend that we see in the industry that helps this trend is disaggregation. So what we see across different technologies is that the system that were built in a kind of integrated way, it becomes now separated. And this is coming from the data center. If you look at the microservices, actually we started by having virtual VMs in a single processor. Instead of having only one application, we started then doing containers, and from there microservices, where the functionality is split at even finer granularity. The idea is that as the components are disaggregated, it's easier to scale. So for example, if some of the aspects need a different scaling factor than others, you can have, let's say, general compute versus network processing, right? The control functions versus the data path. But also through the disaggregation, now the functions can be placed anywhere in the network, right? Trace was talking about the manufacturing, so this would be kind of a local data center or local edge type of thing. Some of the processes can be kind of farther away, right? If you just need some, let's say, IoT device that does not need latency, that can be, you know, at the data center in a region. It doesn't have to be on the plant necessarily. So how that applies to the our discussion today is that optical systems typically had an muxponder, transponder integrated with the optical line system, integrated into an optical system. So what we see now is with this new concept, the miniaturization of the line system plus the disaggregation, that opens up the application of these components to connect routers and connect data centers in a campus, metro, or regional context. So let's look at some of the examples. So typically, or traditionally, better said, we have the chassis. This is kind of the figure on the far left that was connected with gray. You see the gray optics into a optical system that was connecting, you know, double bookended to the other side, and then the process will reverse gray optics back to the router, right? So and these systems are still deployed today. What we see those with the new components is that the whole optical system now can be reduced to a 400ZR type of pluggable that goes directly into the router. So for the simple case where we don't need amplification and we need a lambda per fiber, we can go 400 kilometers with that technology, right? We can move 400 gigs easily. Now, if we want to scale, obviously we need some sort of a FODEM, DWDM, max demaxing, and amplification. So what that is going to bring is a more more efficient utilization of the fiber. We can have maybe 64 lambdas or 48 lambdas now on that fiber. And also that fiber can travel further, right? So instead of 40 kilometers, maybe we can reach now 120 kilometers. What the standards are working, we're talking about the ZR Plus, which is basically building on the ZR technology. What we can achieve with that technology now is the same amplified density, let's say 48, 64 lambdas on a fiber, but now having inline amplifiers, we can extend that reach from 120 kilometers now to several kilometers. What this is, so what you see is here is a very, you know, optimized way to connect routers and transport IP traffic. So if we look at the big picture, what we talked about the ZR, ZR plus. This is kind of the part of the left side. We optimized the connectivity between two routers that need to exchange IP traffic. So we looked at the kind of a point-to-point example of connecting to data centers, for example. However, with this technology, if you look at the amplified case, they're responsible to actually do even small rings, right? The more ROADMs or FODMs you introduce is going to add insertion loss, so the insertion loss, so the reach is going to be lower. However, there is possible to do small rings to have a couple of drops in between the two endpoints. However, if you look at the telecom industry as a whole, there is a requirement to do kind of any service, any rate, anywhere, right? And when I mean any rate is from 1 gig to 400 gig, 800 gig, and anywhere means like it's a couple of kilometers, couple of 100 kilometers, couple of 1,000 kilometers. And also the connectivity is kind of rich, right? So if you, as you move to metro, regional, optical networks is mostly highly meshed type of networks. And obviously, when you move to the core long haul, that's a very specialized type of optical type of network. So what we see is almost a departure where we have some optimization on the IP traffic transport. However, we believe that the other any service, any rate, anywhere optical systems will continue to coexist. Furthermore, what we see is that for the IP traffic, we talked about the disaggregation. We already see in the industry specialized optical line system to actually serve those 400ZR QSFP-DDs, CFP2-DDs in the router, and the full line portfolio of the optical line system is going to still coexist, right? We're going to still need 32 degrees ROADMs and amplifiers for wide applications that continue to exist in the telecom industry. That's all for me, Ref. It's open for questions.
Thanks very much, Tibi. We appreciate it. So, are there any questions, Tibi? Did you have a question, Tracy? I'm sorry. Yeah, please go ahead.
I do. Thank you. That was a great presentation, Tibi. I really appreciated it. I've been trying to get information on the coherent systems. So tell me, I'm still a little bit confused. Can these new coherent systems replace DWDM equipment, or will it live in parallel until a transition is made? Will it allow? Can it actually take the place of existing equipment that is aging at this point?
Yeah, this is a great question, Tracy, and this is where the struggle is in the industry a little bit. But I think what we've seen is a bit of a application specific. So if you look at the ZR Plus in particular, we believe this is very specific to transporting IP traffic, right? So between two routers, right? So the optical systems are way more complex, and there is way more applications that may not benefit from that, right? So that's why we believe that the optimization that started with web scalers are going to slowly move into the CSPs for this very targeted application. However, all the other systems will coexist. And actually, you already see for 800 gig coherent announcements, which it's not necessarily a more effective fiber or spectral utilization, is basically adding to 400 gig to some extent, right? So this is what I think we have the inflection in the market where we're optimize some of the systems, and then the older application will continue to use the systems that are meant for that particular applications on that segment.
Thank you.
Are there any other questions? Okay, no, Tibi, no, thanks very much once again for your talk. So this concludes today's session. I want to thank all our speakers for their time and participation. We appreciate it. Thank you to everyone in the audience who tuned in. The video presentations will be available for on-demand viewing through November 4th. In between sessions, take some time to visit the IPC Networking Lounge in Gathertown to continue the conversation. Join one of our scheduled meetups or start a conversation specific to one of the conference topic areas. You may access the Networking Lounge by clicking on the cup icon in the left navigation bar of the virtual platform. Thank you and have a great rest of the day. We hope you will join us for the rest of the virtual conference. Thanks again.